Now the most natural special scaling, and you might think the most natural scaling would be to divide the circle into 360 degrees and use angle. And of course we could do that. We could go from 0 to 360 degrees, but there's nothing mathematical about degrees, just a historical accident. How is it that we chose 360 degrees? It was a pretty good choice because 360 is evenly divisible by a lot of numbers, and the quotients that we get are really convenient, are often really convenient angles. The most convenient angles will have an integer number of degrees. So there are a lot of good reasons to use degrees, and we use degrees almost exclusively when we're doing right angle trigonometry, when we're analyzing actual triangles, other than maybe certain special angles that we should be aware of. There's nothing at all wrong with 360 degrees, but 3600 would have worked as well, 720 would have worked as well, 1440. So there's nothing sacred about 360 degrees, but there is something sacred about the measure that we use when we're doing the mathematical sine function. So the function y equals sine theta is our most basic function and our mathematical definition. It doesn't use degrees because degrees would get really cumbersome. Okay, we'd have all kinds of conversion factors. Everything would be terribly confused when we start doing a little deeper analysis of the properties of this function. Okay, so what we do is, first of all, we're going to assume for the sine function that the y-axis goes from -1 to 1, with, of course, 0 in between. Now that, of course, implies that the circle that we use is a unit circle. That is, the circle has to have radius 1. If this point projects over to here and this point projects over to here, the distance from here to here is being 1, has to be the same as the distance from here to here, and the distance from here to here is, by doggone, 1 radius of the circle. Okay, so for our mathematical sine function, the circle has radius 1, and the y-axis correspondingly is labeled from -1 to 1. And the values of the function go from -1 to 1. Okay, now the x scale is going to be, okay, this angle here, from here to here. Okay, we're going to identify that angle with how far we've got to go along the arc to get there. Okay, so how far do we have to go along the arc to get to this angle? Well, let's first, it's going to be 5, 6, well, let's observe that. This is our, halfway between 4 and 6, this is our 5th angle out of 16 into which we have subdivided the circle. So the arc here is 5/16 of the total arc around the circle, isn't it? So this angle is going to correspond to an arc of 5/16 of the total arc around the circle. Okay, so we could say this angle is 5/16 of the circumference, or at least the arc from here to here is 5/16 of the circumference. Well, what's the circumference of this circle? The circumference, well, what are the relationships among radius and diameter and circumference? Okay, well, the basic definition that you use throughout, and forget because nobody can ever tell me what the definition is that the ratio of the circumference to the diameter is pi. That is what pi means. It's the ratio of the circumference of a circle to its diameter. Okay. Now, this circle is a unit circle, has radius 1. What's its diameter? I'm sure you've got it. It's 2. Okay, because the diameter is twice the radius is 1, so yeah. If the circumference to diameter ratio is pi, it follows that the circumference has to be 2 pi, or pi times the diameter, which is 2 pi times the radius. So the arc distance around the circle is 2 pi times the radius, this is a unit circle. The radius is just 1, so the arc distance is 2 pi. So we're going to say now that our angle at this point is just the arc distance along the unit circle, which is 5/16 of the circumference, 5/16 of 2 pi. So our angle is 5/16 of 2 pi. And of course we can do the arithmetic. 2 divides 16 8 times, so this is 5 pi over 8. So if we wanted to label this point over here, that would be our 5th point. Here's our 4th point, there's our 6th, our 5th point's about here. According to this measure of angle, this point here would be 5 pi over 8. And our complete cycle goes from 0 to 2 pi. Now, when we use this measure of angle, we can just say the angle is 2 pi. The angle is 5 pi over 8. If we have to call it something, we call it radians. So 5 pi over 8 means 5 pi over 8 radians. 2 pi means 2 pi radians. We don't have to say radians. If we just say the angle is 5 pi over 8 and don't put any units on it, the units are automatically in radians. If you don't put units in your angle, they're in radians. So if you want to talk about a 30-degree angle, you don't call it 30. You call it 30 degrees. If you call it just 30, it means 30 radians. Okay, it's totally illiterate to use like sine of 30 to indicate the sine of 30 degrees. Although if we make a blanket statement saying that that's what we're going to do, then it's not in my opinion very permissible, but I think I'd be overruled by common convention. So default measure for angle is the radian, and the radian is defined just as we've defined it here. It's the arc you would go around a unit circle to get to that angular position. Now there's more to that. We could discuss it a lot further, but that's all I'm going to say about it right now. The mathematical sine function has a cycle that runs from 0 to 2 pi, or if you prefer 2 pi radians. Y value goes from -1 to 1. So when you see y equals sine of theta, this is the function you're talking about. This and no other. Now, I want to talk a little bit more about further subdividing the circle, and one of the really neat properties that the graph of the sine function has that the graphs of the power and exponential functions don't have. It's a deeper mathematical concept, but it's one that's fairly easy to understand.